Next speaker, Christoph Knochenhauer at TU Munich, and he will talk about optimal adaptive control with separable drift uncertainty.
Yes, thank you very much, Christian. First of all, thank you very much for the introduction and for the invitation. It's a great pleasure to be back at KAUST. I was here 3 years ago, but still going by a different name. I got married since then, and my wife was the one to keep her name. So if you have seen my face before but never heard that name before, that's why. The talk today is about, well, it's a story about optimal control of partially observed systems with a little bit of a twist. I think it will serve as kind of a way to whet your appetite for the Wednesday talks. There's a lot of control and partially observed systems there and filtering techniques. So if you like what you see today, be prepared for Wednesday. If you don't like what you see today, still go there, because then you can see how things are done well. So what's the point of this work? It's joint work with Sam Cohen from Oxford and our PhD student, or former PhD student, Alex Merkel from TU Berlin. And the idea comes from a problem in finance. Just to set the scene for you, here's a very, very simple example. Suppose that you have a price of some financial asset, P, and you're in a setting where your trading impacts the price. So if X denotes the inventory, then you can control your inventory by choosing a trading rate U. And now the assumption is that the price shifts depending on your trading. So that's a simple price impact model with permanent price impact. And then you want to maximize something. Yeah, you want to get rich by controlling your risk. Doesn't really matter what kind of criterion you write down here for the sake of this example. More important for me, for the talk, is I want to focus on this price impact parameter that you see here. In practice, that's something that you don't observe, right? You have discrete data, so you will only see this affected price on discrete time steps, and it's very challenging to estimate this lambda parameter, this price impact parameter, because you don't know if price changes come from the Brownian motion that you have in the back, or if they come from this unknown parameter. It's hard to disentangle. And what makes the situation here even worse, you have control over the ratio between the signal, so the lambda times u. You can make that larger in comparison to an increment of the Brownian motion by choosing a large value of u, or you can make it smaller. So you're controlling how much you see of lambda, basically. But that is not your main objective. So you could use your control to see more of that unknown parameter. But your main objective is to get rich, right, in this setting. So that might contradict each other, and you have to find a way to balance this. And this is what this talk is about. So in general, what I wrote down on the previous slide is a very simple linear quadratic control problem. We know how to solve them. But there is a very challenging trade-off between actually estimating the parameter, the value of lambda, and optimally controlling your system. So it's in some sense an exploration exploitation kind of trade-off. You want to choose u large so that you see more of the unknown parameter, but maybe not too large, because that would make your position too risky. So formally, this is a stochastic control problem with partial information or partial observations. And what makes it particularly tricky is that how much you observe of the unknown state depends on what you're doing. And that's what we would try to solve with this paper. Embedding this more into the literature, we say here that the so-called separation principle fails. So in many of the partially observed control literature, you will have what is called the separation principle. It takes many different forms. You can think of it as it is possible to separate the problem of estimating the state and actually controlling. And so you're first doing the estimation, and then you are in a setting where Your information doesn't depend on the control. And then you just do your usual control type of arguments. Here, this does not work. And then the main questions that we ask ourselves is, does the usual machinery still work? Do we have something like a dynamic programming principle? Can we solve the problem by solving a Hamilton-Jacobi-Bellman equation and so forth? Yeah, we'll get to that later. If you look at the literature, people do study these types of problems where you have controlled information, but they usually formulate them in some form of weak sense, which it could be something like you're not just choosing U, but you're also allowed to choose the probability space, the Brownian motion, and the filtration that you are working in as part of your control. And this is usually done in a way so that the separation principle is restored so that you can separate estimation and control. And that's precisely what we don't want to do in this work. And we don't want to go to a weak formulation. We want to formulate it with a fixed probability space, fixed Brownian motion, fixed filtration that we start out with, and then see how far we can push things. I'm aware of 2 other papers that do this. One is by us, that's a follow-up. And the other one is by Cox, Kelblatt, and Wang. That's also a follow-up of our paper. All right, so let me set the scene. What's the exact problem that we are looking at throughout this talk? It's a simplified version of this price impact setting. So our controlled state process is now denoted by Y, and it takes the form Brownian motion plus random variable lambda, and then you integrate your control to get to the current state. The objective here is just taken to be quadratic in the state and in the control. Finite time horizon can be generalized, no problem. Main assumption, we only observe Y, and we don't observe lambda and the Brownian motion individually. So this means if you're choosing your control U, they have to be adapted to the filtration which is generated by your state process YU. And the problem is, of course, just by observing Y, you cannot distinguish between changes coming from this one and changes coming from this one, so you have to do some estimation. And most importantly, if you choose a different control, you get a different filtration. For example, if my control action is to do nothing, I choose it to be equal to 0, I won't learn anything about lambda. If I choose U very large, you can see that the drift component here dominates compared to the Brownian motion. I see more of lambda. That's the intuition behind the setting. Yeah, and of course, it gives me different information depending on what I'm doing. And yeah, as I said, so we don't really, this is the strong formulation. We don't really know any papers who study this kind of formulation because the separation principle fails. And then you have this trade-off between trying to optimize this cost functional and choosing your control in order to learn. And it's hard to quantify how well changing your filtration affects the cost function. This is what makes it tricky. In the paper, we are slightly more general, but for the sake of this talk, we stay in this very simple form of the state process and just quadratic cost function. So how does one do this? We start with what one always does in this partial information setting. One tries to rewrite the state dynamics in terms of observable quantities. Here, this is our starting point. Changes in Y are this is the drift, this is the Brownian motion. And now I want the left-hand side, I can observe. The right-hand sides, each component individually, I cannot observe. So the first thing I'm doing is trying to rewrite the first component by projecting it onto the information that I have available. And how do you do that? Well, you're projecting it on your filtration. So I take the lambda and replace it by its conditional expectation. In order for this identity to hold, I also have to subtract it. But the first component is now observable. I'm choosing U myself, and this one is projected onto my information set. So yeah, this one is fine. The remainder, we don't care about for now. We just plug that into one process. And this is the magic of filtering theory. in our filtration, in our observation filtration, the remainder turns out to be a Brownian motion. And now I've rewritten my state into observable quantities. The problem here is that if I want to apply some form of dynamic programming, I want some Markovian representation of this conditional expectation here. So I have to put in some extra work to get a nice representation. And we are in a very lucky situation where you can actually write this conditional expectation as a nice Lipschitz function of two auxiliary state processes. And so what we are doing is we're just replacing this by this function of these two other processes. Why are we lucky? Because usually there are just very few situations where you can describe this conditional expectation in terms of finite dimensional states. Usually this turns out to be infinite dimensional. We are lucky because we chose to be lucky. Yeah, that's precisely what we wanted to. We didn't want to deal with control problem in infinite dimension. Okay, so if you write down the dynamics for these auxiliary states, so basically what you have achieved is now you have a system where each of the components is observable in your components, in your filtration. The cost for that is that our state process is now three-dimensional instead of just one dimension. It's the cost we have to pay for that. But that is a nice Markovian setting, and that's what you usually do. If you have the separation principle, then what would happen is that, well, the filtration becomes independent of the control, which does not happen in our setting. And the Brownian motion, the new one, also does not depend on the control. In our case, it does not hold. The Brownian motion that drives the system and the filtration, they still depend on the control. So it's still a non-standard control problem, but now in full information. Okay, what about related work? It is closest to work going back to the early 90s from Benesch, Kratzer-Schrichel, and Cohen. They have essentially the same dynamics as we look at in this talk, at least. The cost function is a little bit simpler. And what they do in contrast to us is they have some kind of a weak formulation. By weak, I mean they are constructing their state process by a change of measure. And in particular, what they do is they fix the filtration in a way so that it is independent of lambda. And this seems a bit odd given what we are trying to achieve here, right? Because the filtration is what models our information. And if it's independent of lambda, that means we're not learning anything new along the way. Why are they doing this? I mean, these are very clever people. You know their names. There must be a good reason why they do this. It's because they can show that in the strong formulation, so ours, there's no optimal control, but in this weak formulation, they can find. There's also related work, 2018, so this is more recent, Bandini, Kosov, Fuhrmann, Pham. They also start out in a setting where you have controlled information, and they then recover the separation principle basically by introducing additional randomization. On top of that, I am not aware about any literature that looks at this control-dependent information setting in strong formulation, at least in the mathematical literature. I'm not sure about the engineering side. There's probably some work there, but the mathematical literature is very, very limited here. All right, let's try to figure out why. So why is it so difficult to work with this problem? Let's start with what we usually would like to do. We want to apply dynamic programming arguments. This means that instead of just looking at this one optimization problem, we're trying to minimize the cost. We are now introducing an entire family, and we are indexing that by initial time and initial state. For each initial time, initial state, you write down the problem. And then you try to link this family of problems by the dynamic programming principle, which essentially just says that instead of optimizing over the entire time period, you are allowed to chop it into two smaller pieces. optimize on each sub-intervals independently and then paste together your optimal controls, and this gives you a globally optimal control. That's one way to think about it. And if you make the first time interval smaller and smaller, let it go to small t, then this transforms into a PDE or your optimal cost for this function v, your value function v. And this is what we usually work with. You write down this Hamilton-Jacobi-Bellman equation, solve it, and then from there go back to the original problem by some Feynman-Katch argument in order to solve the problem. And in our setting, this turns out to be difficult. We were really, really unsure if dynamic programming works at all. The reason is the following. Our controls are, the set of controls is just evil. Yeah? By this, I mean the following. Consider two different controls, U1 and U2. They take values in some set, but the most important feature that they have is they must be adapted to the filtration that their associated state generates. And now I pick some arbitrary time, tau, that could be a deterministic time somewhere in the future. And now I decide to follow U1 up to time tau, and then I switch to to control U2. And this easily fails to be admissible. Why? Because U2 on that second time interval might need information that it generated itself beforehand, before time tau, but which maybe U1 hasn't generated. So if there's any kind of path dependence in one of the controls, then this will immediately fail to be admissible. If these are just feedback controls, so functions of the current state, that's not an issue, but we allow for general controls. So this just fails. You cannot just paste arbitrary controls. And that's the basic, the minimal requirement that you need for dynamic programming. Because that's what dynamic programming means. You construct two optimal controls on two subsets, you paste them together, and then it's globally optimal. And a priori, you cannot tell which ones you can paste and which ones you can't. That makes it tricky. Yeah, there's more issues. So if you take the sum of two controls, you don't know if that's still admissible. If you have sequences of controls and pass to the limit, then you don't know if the limit control is admissible because it always depends on the filtration. And it's just tough to work. Yeah, so the story is that the reason why no one works in the strong formulation is because you just can't. All the standard techniques that we have, you cannot just apply. Yeah, you have to come up with a way of solving this problem without actually touching the problem. Yeah, you can't use your standard techniques because nothing that you usually do is allowed because you don't know if you're leaving the set of admissible controls. The reason why I frame it this way is because that's how we solve it. Yeah, so we try to solve the problem without touching it. How do you do that? Well, you approximate it from one side, you approximate it from the other side, close enough so that you get information about the object that you're interested in. Before we get there, I should maybe talk a little bit about why we actually want to do this. So on the one hand, it's a nice, challenging mathematical problem. So for some of us, that's probably enough to have a look at it. But from a practical point of view, why don't I use any kind of weak formulation where I don't run into that much problem, which are just more tractable? And that's one of the arguments that speaks for a weaker formulation. If I'm doing some kind of weak formulation, which, as I said, could mean something like you choose your probability space and the Brownian motion and the filtration as part of your control, that even enhances the chances that you can prove existence of an optimal control, because you just have more controls available to choose from, richer class. And it doesn't really violate the information pattern that we are imposing on the problem. If you're in some weak setting, think weak solutions of the state dynamics equations, the SDEs, and it's just basically adding external independent randomization or independent information to our filtration. And that does not violate what we want, and namely just not being able to see lambda and the Brown motion directly. So external information is not a bad thing. It doesn't violate what we are trying to do. Yeah, so that's why you may want to do the weak formulation. That's the case for it. What is the case against the weak formulation? In reality, your Brownian motion is fixed. Yeah. You will have a tough time. So, and I'm not speaking to an academic audience, I would say, you will have a tough time explaining to your boss why the trading strategy that you're constructed works on only for a particular Brownian motion. Does that make sense? I don't know. Because the real system, the physical system that you're controlling, the noise is fixed. Yeah, and you kind of just swap it out against something else. You might ignore that if you want to, but that's something to keep in mind. You possibly need a larger filtration. So if you're in this weak setting, you may add independent noise to that, external randomization, if you will, and that's a larger filtration. You may not want that. Why should I start flipping coins along the way just to solve the problem? Here's one key point. So the first two I don't think are that serious. It's more on a philosophical level. The third one might actually be an issue. The weak formulation, if you are now choosing probability space, Brownian motion, whatnot, in addition, you just have a larger set of control. And this might lead to a different optimal cost. Strong formulation and the weak formulation might have a different cost. And if there's a difference, then you should be very careful. We don't expect it to be, because even in the 90s, it was shown for this special case of ours that weak and strong formulation lead to the same cost. But as I said, their weak formulation is kind of odd in some sense, in that the filtration, so your information is independent of the lambda, which is the thing that you're trying to learn along the way. So this kind of contradicts the filtering idea. And you might have to accept that if you're going with the weak formulation. So the point here is, at least to me, I don't care which formulation you choose, but you should be aware that there's a difference. And in order to make a good decision on which formulation to choose, we actually need to understand the stronger formulation better. If there's a particular difference between weak and strong formulation, then maybe you're forced to work with the strong formulation. If we know that the weak and the strong formulation lead to the same optimal cost, you're free to use the weak one, because that's more tractable. That's all we need to start. Okay, so how do we do that? Let's check time. Looks good. Here's the program, the agenda. What we want to do is we want to characterize this value function. So the optimal cost parameterized in terms of initial time and initial state as the unique solution to this Hamilton-Jacobi-Bellman equation. In other words, we want to show that even in the strong formulation, dynamic programming still works as you would expect it to work. In addition, we want to show that the optimal cost in strong and weak formulations coincide. And we want epsilon optimal feedback controls. That's a strong indicator that if you are doing numerics in the strong formulation with your usual techniques, I don't know, based on the Hamilton-Jacobi-Bellman equation, that you're actually solving the strong formulation problem, right? And just the weak one. But like this. What's our main tool? We use a tool that Benesch, Karazas, Bischel, Cohen didn't have back then, namely the stochastic Perron method. Goes back, early work was by Ragnar Sirbo, 2012-13. The idea is to not work with the value function or the problem that we want to solve directly, but approximate it from below by a nice enough class of functions, problems. So we're looking for a suitable approximation from below, which converges to a super solution of the PDE in the viscosity sense, not so important here. Then we do the same thing from the other side, look for an approximation from above and show that it is a subsolution of the PDE. And then we show that the PDE satisfies a comparison principle, which means that subsolutions are smaller than super solutions. So the approximation from above is smaller than the approximation from below. And then this just wraps our value function, our problem, somewhere in the center as the unique solution. And then you just have to think about what are good approximations. For the approximation from below, we'll talk about weak formulation in a second. For the approximation from above, we talk about piecewise constant controls. And then the comparison results is standard. That's just PDE here. Approximation from below. Now I formally define what I mean by weak formulation. There are many, many different ways that you can formulate a stochastic control problem in a weak sense. This is probably among the most general or weakest ones that you can come up with. The idea is roughly you fix your initial data, Tx. You can still choose your control, but now in addition, you also choose your probability space. You choose your filtration, satisfying the usual conditions. You choose the Brownian motion yourself. And then you want X to solve the SDE on that probability space with that driving Brownian motion that you are choosing yourself. So essentially, we are looking for weak solutions of the SDE. Yeah. All possible weak solutions. We can choose which probability space we want to live in. And compared to the earlier formulation where the probability space was fixed, and the Brownian motion that we started with was fixed. Yeah, so this means that here, if we're looking for weak admissible controls, there's just a larger class, because we can always go back to the original probability space and Brownian motion that we started with. We have more controls, so the value, if you're minimizing the cost over weak admissible controls, is smaller. So this will be our lower bound. And the advantage here is that now we've broken this evil cycle of, well, we first have to choose the control, then we solve the SDE, and then the SDE gives us the filtration, and then we have to make sure that the control was actually adapted to that filtration. This is now broken in this weak setting because here we fix Brownian motion, filtration, fix U, and then we solve the SDE. So this is a lot easier. Yeah, this turns out to be a standard problem, so we can do the viscosity super solution characterization in a classical way. The way that we do it here is instead of just the ones where we have the probability space and the Brownian motion fixed. That's why it's smaller. You can always restrict to those which are on the original space with the original Brownian motion. That's why. Yeah, so that's a simple argument. So now this weak value function, the V weak, is also approximated from below by something of which we can show that it is a super solution of the PDE. This can be done as follows. So there are many ways to do this. This is the classical one in the stochastic Perron setting. You're writing down the set of all functions V minus, which satisfy some continuity and growth conditions. We want them at terminal time to be smaller than our value function, just smaller than the terminal payoff that you get. And we want that if we plug any state process corresponding to any initial condition and any weak admissible control, if we plug that into the function and add the running cost, then this is supposed to be a submartingale, strong submartingale, meaning that the submartingale property also holds at stopping times. And then you can very easily show the submartingale property and this terminal condition. They guarantee that any of these functions will be smaller than the weak value function, which is smaller than the value function in a strong formulation. But you can also show that if you now pass to the pointwise maximum of all of these subsolutions, stochastic subsolutions, they turn out to be a super solution of the PDE. And at terminal time, they are larger than the weak value function. Since it's the supremum of something which is smaller at terminal time, they're actually equal. And that's why it is called the Perron method. The Perron method is a classical way of constructing solutions of PDEs. What you do is you look at all super harmonic functions of the PDE and show that their minimum is also a subsolution. This is pretty much a stochastic analog of that. So now we have an approximation from below, which is a super solution. And this here is standard, because we are in this weak setting, so there's not much going on here. The approximation from above, this is where things got tricky. And we actually thought a lot about how to do this, because here you cannot switch to the weak formulation, because weak formulation pushes the cost down. So we have to stay in the strong. Starting point, we restrict to piecewise constant controls because they are easier to deal with. So you fix interval length of delta, and then you only look at controls which are piecewise constant on a fixed grid of length, where the subintervals are of length delta. So something like this over here. And then you can just minimize over all of these piecewise constant controls, where interval length is delta. This is denoted by v delta. And since this is the restriction, the associated value function will be larger. Problem is that doesn't fix any of our problems because we're still in the strong formulation. Pasting doesn't work, so doesn't help. But now comes the crucial trick. Now we introduce a new alternative stochastic control problem, where we're looking at piecewise constant controls, and we just go ahead and fix the original Brownian motion. So we're not allowing it to switch now with the control. We fix the filtration as being the augmented filtration generated by that one fixed Brownian motion, and try to solve that problem. Piecewise constant controls, but Brownian motion and filtration are now fixed. The value function corresponding to this is now v hat. The problem is, since we're switching out the Brownian motion, and it's exactly the kind of thing that we are trying to understand, we don't know how that relates to the things that we are actually interested in for now. But what is nice about this problem is that this is pretty standard. Piecewise constant means that you can embed it into a discrete time control problem. And the assumptions that we are imposing are nice enough so that you can really solve this quite easily. You can show that piecewise constant with fixed filtration and Brownian motion has an optimal control. And the important thing is in feedback form. Feedback form means that the optimal control can be written as a function of the current state. It does not take into account any past information. And you can imagine that pasting those could work. And that's the trick. So now we have an optimal control, optimal piecewise constant control for the auxiliary problem. We take the function, which gives us that feedback form, and we plug that into the problem with the control-dependent filtration and control-dependent Brownian motion. We can do that just switching out the Brownian motion and the filtration. And that's admissible. And then you have that the SDE has a solution which is unique in distribution. So the state has the same distribution, which means it has the same cost. This means that we have found an admissible piecewise constant control for the problem with piecewise constant controls, but with control-dependent Brownian motion and filtration. We don't know if it is optimal. We don't care, because it might be that there's even a better one, which tells us that the problem with control-dependent filtration and Brownian motion is a smaller value than the easy one. So now we have a nice tractable upper bound that we can work with. And from there, it is straightforward to show that if you send delta to 0, this will converge. I think we even show that it converges to a solution, not just a sub-solution, using standard Balzuganidis viscosity approximation scheme arguments. This is easy at this point, because now we have something tractable to work with. Time for step 3. We show that if we have a super solution and a sub-solution of the PDE, which compare at terminal time, then the super solution is larger than the subsolution. This is a pure PDE theoretic argument. This is standard, doesn't care about any information structures. This is easy. For us, this means that our approximation from above, which was the piecewise constant approximation, must be smaller than the approximation from below, which was this weak admissible control approximation. But the V minus was by construction less than the weak value function, which is by construction less than the strong value function, which is by construction less than the piecewise constant approximation from above. So you see that we have this chain of inequalities, they must all be equal. Moreover, we know that the V plus, the approximation from above, is the limit of these piecewise constant ones in value, even with the auxiliary control problem. So with the Brownian motion in the filtration. What does this mean? The V plus and the V minus, they are upper and lower semi-continuous. So if they're equal, they must be continuous. So our value function is continuous. One is a subsolution, the other one is a super solution, but they are equal. And so there must be a solution, and they are equal to the value function. So our value function is unique continuous viscosity solution of the HAB. We have it characterized in terms of dynamic programming without ever touching that thing. Moreover, weak value and strong value coincide. And finally, these feedback controls, these piecewise constant feedback controls, they form a sequence, a minimizing sequence, which converge, or whose values converge to the optimal value. We don't know if the controls themselves converge, but we don't care. Because we know there are certain specifications of our model where there are no optimal controls at all. So that's the best we can get. And that's it. So these are the main results that we got. A little bit of conclusion and outlook. So inspired by a trading problem with price impact, we look at a stochastic control problem with partial information. And the crucial point is we have control-dependent information. And we formulate everything into strong. We show that strong and weak formulation lead to the same optimal cost, establish PDE characterization, and construct a maximizing sequence of controls, or minimizing sequence of controls, sorry. We do have numerical examples in there showing that you can actually compute these piecewise constant controls, which should not be too surprising, I guess, but it's a toy example. The outlook is, well, we actually want to solve something which is more of more interest than our toy example that we have in the paper. So in particular, especially I want to solve the trading problem. But yeah, it's tough to solve the PDE because you end up, at least in the formulation we had, in a fixed 5+1 dimensional setting, and then Alex didn't have enough time before finishing his PhD to look closer into that. So it's up to me to do that eventually. And then finally, we're looking into infinite dimensional extensions. So for example, where you take lambda not just to be a random variable, but this might be an entire process of time, and then things get more complicated. The extra states that you get are infinite dimensional, and then things become more complicated. Thank you very much for your attention.
Thank you very much. Are there questions or comments?
Thanks a lot for the talk. I was wondering, with respect to your final bullet point, the extension to infinite dimensional spaces, maybe I was thinking of another extension where maybe start from this optimal trading problem, but now you add a transient impact.
Yes. Yeah.
Which is weighted by some.
That's actually what we started out with in this transient kind of setting.
But you had like an exponential kernel, I think.
Yeah.
So now if you replace it by a more general kernel, do you have any ideas on how we could maybe solve this?
That becomes tough. So there are many technicalities along the way. I think the filtering bit still works. You will be forced to work in an SPD setting, optimally controlled SPDEs. And then the main question is, so our program relies heavily on this comparison principle for the PDE. And I'm not sure if there are strong enough results for this particular situation that you have in mind to get there. Approximation from below and above should still work in the same way with the same ideas. That's also what the follow-up paper of Alex Cox and Secretary what they are doing. But they're looking at the very particular situation where they already know that they can have this comparison principle for the PDE that they end up with. So I think this is the bottleneck. You should look for another approach, probably. So that's probably you will be more successful compared to. I mean, people have been trying to do this infinite dimensional PDE viscosity theory for a while, and they always struggle with the comparison principles, right? So I would look for a stochastic argument. That's a guess. Go to something with more structure so that uniqueness becomes easier.
Other questions? Not, then let's thank Christoph once again.
Thank you very much.